let's say you're collecting eggs. And for fun, instead of being chicken eggs, let's collect dinosaur eggs. So we can collect 6 eggs from our Parasaurolophus, and we can collect 4 eggs from our Triceratops. So if we put our eggs in our bucket, will the sum of the eggs be divisible by the same number as the individual groups of eggs? We have a group of 6 eggs here and a group of 4 eggs here. If I want to see about dividing by 2, and if I take 2 eggs away from each group, can I do that in an even amount so that I do not have a leftover egg? For the case of the 6 eggs, I can reach in and grab 2 eggs at a time. And I can do that until there are no eggs left. In the idea of division, this means that I took 6 and divided by 2 and had a remainder of 0. Looking at the 4 eggs, I can reach in and grab groups of 2 and also end up with an empty basket, meaning that I've divided by 2 and have a remainder of 0. Starting over, if I had put all of my dinosaur eggs into one basket, then I can again pull out groups of 2, meaning I'm dividing by 2. And I can do this until my basket is empty, meaning my remainder is 0. I had 6 in one group, 4 in the other, so a total of 10 eggs. So 10 is divisible by 2 also. If I had a different scenario where I had my Parasaurolophus eggs were a total of 7 instead of 6, then trying to take groups of 2 here, I'm going to end up with 1 left, meaning that 7 divided by 2 has a remainder of 1. It's not evenly divisible. What we're looking at is counting numbers. I can count a number of items. These are also known as natural numbers. I want to know if I take natural numbers and I divide by a natural number, do I have a remainder left? If we start back with the 7 and then add the second group of eggs, the 4, I will again have an odd number. I will have 11 eggs. If we try to divide by 2, we will also have a remainder. With our 11 eggs, if I pull out 2 at a time, I can do this up to a certain point, and I have an egg left in my basket. This is a remainder. It remains in the basket. This is the essentials of the ideas of dividing natural numbers. Now that we've looked at the practical way of dealing with division and the sum of terms that are going to be divided, we are going to do this in a more abstract way and prove this situation. So the notation we have here is that A divides B. Another way that you could write that would be as a fraction, and this fraction would be of this form. A will divide B, and the intention is that this will be some other number, a single number without a remainder, so there's no decimal point. So this would be some other number n, where n is a natural number. Also, we have A is dividing C. So in our example before, when we started, we had 2 was the number we were dividing into. We were taking groups of 2, and we started out with 4 and 6. So B and C are like 4 and 6. So that was a realistic example. Now we're going with an abstract example. Then we're going to say that A will divide the sum of the two previous numbers. We saw that happen too. When you add 4, you add 6 together, you get 10, and 2 still divided 10. And then the last statement here, we're going to just make a note that A, B, and C are going to be natural numbers. These are counting numbers. It's the things that we can count, like eggs and rocks and dinosaurs and chickens, things like that. We also need to note that A is not going to be 0. We're not going to try to take nothing out of the basket. So division by 0 with a classical algebra is not allowed to be a divisor. To write this proof, we're going to take our if statement as true and then show that our then statement is a consequence of this. Since A divides B, that means A is a factor of B. We're going to write B equal to AK, where K is going to be just another integer. And we're going to do the same thing for C over here. So we're going to call C to be A times L, B to be A times K. Now we can see that if we would rewrite this again like a fraction, if this is B divided by A, since B is equal to AK, then we would have that this fraction's equivalent to AK divided by A. This is a reducible fraction. There's an A in the numerator and denominator. Those would divide out. That would give me 1 times K, which is K, divided by 1, which is just K. This was matching the idea of the example that I gave before. Since K is an integer, we see that we have a complete division without a remainder. There's no decimal here. The same thing would happen with C down here. If we rewrote it as a fraction, we could show that it reduces out to just the factor L. So we've demonstrated that B and C here can be rewritten so that we can demonstrate the divisibility without remainder. Now we need to see what happens when we add B and C together. So we've taken the if statement as true. We know that these are going to be true if we have these conditions because of the way division is defined. So now let's take B plus C. B plus C has to equal AK plus AL. If we take the left-hand sides and we add them together, then we have to take the right-hand sides and add them together. But then notice that there's a common term of A, so we can factor that A out. If you know what the distributive property is, we're essentially reversing the distributive property. We also want to note, and we haven't discussed that quite yet, you see the demonstration with the eggs, that when we put the two groups together, they're still a group of eggs, right? If these are both natural numbers, if you add natural numbers together, that result, that sum, is going to be a natural number also. That would this demonstrates closure for addition of the natural numbers, and that's a separate concept which you could go into further discussion with or study with. If you study contemporary algebra, that is certainly something that is a very important topic when you look at algebraic structures. But for now, we're just going to take this as we understand that when you take two counting numbers, you put them together as addition, you're going to get another counting number. Okay, so in our example, it was 6 plus 4 gave us 10. 10 is a counting number. We can count 10 eggs. We have 10 fingers, 10 toes for the most part. So now we have this quantity here is a counting number. multiplied by a, and that was b plus c. So this is some quantity. Again, b and c, we started out, we were told they are counting numbers. So this sum right here is a counting number. It's a natural number. This sum right here is a natural number. So we have a natural number equals a times a natural number, which is exactly what we had here. And we said that we know this by the definition of division, that this should be true. That since a divides b, a has to have a factor, or b has to have a factor of a inside of it. And we see that this natural number has a as a factor inside of it, meaning that a divides this sum. And that's exactly what we wanted to show. We wanted to show that if we started with these ideas, that we could naturally come to this conclusion. We have that statement right here, so we are done with this proof. Hopefully this has helped you with understanding how these proofs work, especially with seeing a physical model of that just out of nature. Hopefully you find some other mathematics in your part of the world to enjoy. Cheerful calculations.